Well, we've had two talks in a row about OVS DPDK offload with RTE flow, and now we've got to talk about kernel-based offload with Simon Horman from Netronome.
Thank you. So today I'd like to give just a little bit of perspective on the kernel-based offloads, maybe a little bit of history behind them, then a quick summary of the features we have. Quick summary of the features and maybe look into the future a little bit. So who am I? I've been contributing to OVS in the kernel for quite some time. And I'm currently work with Netronome. I'm the offload architect there for the OVS product, and I also coordinate all the open source activities at Netronome. So I already went over the agenda. Let's get into the body of the talk. So historically, switching has been done on dedicated hardware, black box if you like. It tends to be very fast, but it has a fairly fixed feature set. You buy the switch and it does what it does, and that's where you are. So it's inflexible. When virtualization came along, to some extent, switching moved into software because people started running effectively switches in the hypervisor to switch between the VMs. This has essentially the opposite properties. It's very flexible, especially with something like Open vSwitch, which is open. We can modify the feature set at any time, but it's relatively slow. So then SRAV moved switching on the host back into hardware. So effectively, the NIC has a fairly rudimentary switch, which is able to move packets between various ports and the host. Performance improvement is vast, but the loss of flexibility is similar. You know, what one simply, well, at least when this technology first became available, there was pretty much no scope to increase its feature set. So what we see today with SDN is people demand a fairly rich feature set. I have a summary of some of the features offered by something like OVS. But running this in software, again, is slow. So from my point of view, working with a vendor that makes offload solutions, the promise of hardware offload of something like OVS is to combine the best of both worlds. So we can view this, and I took this idea from Rashid actually, as a pendulum swinging backwards and forwards, where on the one hand one side we have hardware which is fast and inflexible, and on the other side we have software which is slower and much more flexible, and in the middle we have the best of both worlds, and that's kind of the reason that there's so much interest in this area. And so this is a fairly arbitrary but real performance numbers. We took some Intel CPUs and we run the DPTK, and then we took the Netronome NIC. And essentially what this is trying to represent is that for vastly less CPU consumption, we get markedly better performance throughput. And the reason these converge would be that the packet size is increasing. So at some point, the DPTK can reach line rate. Oh, I am going quite quickly here. Okay. So let us look at the kernel-based offload architecture. This is in contrast to the DPTK offload architecture, which was covered in the previous sessions. So Netronome, and in general, there's a long history of attempting to make an offload solution for OVS. And one possible approach is to actually look at the OF proto level and essentially design a piece of hardware that can talk OpenFlow and offload there. This is pretty nice because the switch or the implementation running in the hardware can take a very holistic view of what's going on and provide a very nice offload based on what's going on in the system. The downside is this is essentially it needs to implement all the features of the switch. Or in other words, there's no fallback path for flows that aren't offloadable. Either it can do everything you need, or it's lacking. So then the next kind of evolvement in the next solution that Netronome came up with, which is publicly available but is not upstream, was essentially to hook into OVS kernel data path at certain points. And when it would, for instance, see a request to add a new flow, then it would reflect that request both in the software, which is the existing path, but down into hardware. So flow life cycle management, but also statistics were handled in this way. This was, I have to say, a pretty nice approach. I say that partly because I wrote at least 2 implementations of this. It had fairly minimal impact on the code in terms of it didn't add much more code. But it was ultimately rejected because it failed various criteria that were set for upstream acceptability. And what are these requirements? So the first requirement is that all features of hardware offload must also be implemented in the software data path. And the hooks approach actually does meet this criteria, perhaps in unobvious ways. The second criteria where the hooks fell down was it must also be useful more generally. And these requirements came from the upstream kernel community, not from the OVS communities. So they were really looking for something that would not be OVS specific, that had some potential for reuse. And after much debate, TC-based data path was deemed to be the best way forwards. It reused existing infrastructure. It meets the top 2 criteria. And that essentially is the solution that we have today. So let us look a little bit about how things work without offload in the kernel, and then we'll look how they work with offload. So we have several components here. At the top is the user space OVS vSwitch D. At the bottom is the data path, which is implemented in the kernel in this case. And then on the side, we have the VMs, which we're trying to supply packets for. So when a flow comes in that the data path doesn't know anything about, we get flow miss. And then user space programs the data path to know this flow. This is the mega flows put into the data path, and it also forwards the packet through the data path. It then gets delivered to the guest, usually using Virtio. So how are things once we add offload to this? Well, more complex. So effectively, what we have now is 3 different data paths. We have the original kernel data path, which is still functioning, but it's now only used for fallback traffic. We have the TC data path software implementation. So that's part of meeting the upstream requirement that anything that is implemented in the hardware must also be implemented in the software. And then we have the hardware data path itself. When a miss comes in, things are more complex. Firstly, the miss occurs in the hardware data path, and then it goes up to the TC software data path, which is typically not populated. And then it goes to the OVS kernel data path, which could process the flow if it knew about it, but if in this case it doesn't. So we use the existing fallback mechanism, or the flow miss mechanism provided by the OVS data path. And then it programs the flow. Now, some flows can be offloaded and some flows cannot be offloaded. It depends on all sorts of criteria, including perhaps the hardware is full of flows already, so it can't accept any more. Perhaps the flow includes some match or action that the hardware does not support, and so on. So in that case, if it can't be offloaded, it goes to the software data path, the OVS kernel data path, the original one, and that works pretty much the same way as it would, well, actually exactly the same way it would without hardware offload. But for flows that can be offloaded, which is the point of the system, They are programmed via TC in the kernel into the hardware. And similarly, statistics are retrieved. Usually the hardware is actively sending statistics to the kernel, which then stores them, and then when users want to find the statistics, it reports them to the user. Okay, so yeah, sorry, I already spoke of step 3. So now the packets can basically be forwarded through the system without having to go to software at all. And this is kind of the promise of offload, that the packets are forwarded without any cost to the CPU. And then they would typically be delivered to the guest by the NIC, either using SRAV, so it's to deliver straight using a VF into the VM, or you can use the intermediate of using VirtIO, where effectively you have the hypervisor on the host is running some kind of application that is getting packets from the card and then forwarding them onto the guest. Now the advantage of using this kind of VirtIO system over SRAV is twofold usually. One is it facilitates the live migration feature, and another is that it allows a vendor-neutral driver to be installed in the VM. So if you're in a VNF environment, the VNF provider or the VNF vendor may only support a certain number of drivers in their VNF. Generally, VirtIO is one of them. So it's more portable, if you like. Okay, so now I will do a quick, maybe not so quick. I will now go through the evolving feature set of the kernel-based offloads. So I won't read this all out, but the general gist is back in 2.8 and actually overlapping into 2.9, the basic feature set was introduced to allow you to do flow offload. So you can see that things started fairly simple, matching on basic fields like the addresses in the MAC header, the addresses at the IP level, and things like UDP ports. Also tunnel metadata, which is required for offloading tunnels. VXLAN was the first tunnel to be supported. Geneve followed not so long afterwards, but it was quite a bit later that support for Geneve options was added, which is a requirement for use with Alvin. We can see that as time's gone on, the number of matches has increased, that there's been incremental improvements adding missing options at the IP level. See that more tagging has been added, things like MPLS and Q&Q. We see that tagging has been fixed multiple times. VLANs seem to be very simple, but also very complex to get right. And so on. We can also see, perhaps it's not obvious from this, that we've generally moved from fairly simple offloads to more complex ones. So I'm particularly talking about in the tunnel column where we get into things like ingress ports, not the rate limiting, but the tunnel endpoint on the bridge, which facilitates one to do offloads in situations where we are bonding the physical ports using Linux bonds. We can also see that things are slowly moving from stateless things, matching on an IP header and then forwarding a packet, towards more stateful things. You see the QoS is listed here. So where is this going? Looking into the future, or maybe not so far into the future. There's been great work done recently on contract and NAT support. I entirely expect this to be useful within, say, the first quarter of next year. When I say useful, I mean upstream and able to be used. I believe we will see more QoS. There's fundamentally 3 QoS features supported by OVS. One is egress port rate limiting, which is already supported by this solution. Sorry, ingress port rate limiting. There's also egress shaping, which allows you to classify on a flow-by-flow basis the shaping that should be applied to flows. And then there's metering, which is, well, it's somewhere in between, because it's a policing solution that works flow by flow. I also believe that VDPA is a very interesting technology in this area because it allows hardware offload of the VirtIO solution. So we can have vendor-neutral drivers. We can potentially support live migration. But we can do so in such a way where the VNF vendors only need to support one driver to cover a very wide range of hardware. So, seem to have once again finished early. Thank you very much for your time. Take any questions you have.
So do you know, like for OVN, for example, what offloads, if any, are missing other than the connection tracking that is in progress?
So yeah, my understanding is connection tracking is the big one. I haven't looked far beyond that, but I would think that's probably it.
So, so as Simon explained, to have offloads in OVS, it's actually a two-step. It's a two-step process. The first step is to have TC supported in the kernel, and then the drivers can implement their hardware offloads of the TC commands. So the first stage. So regarding connection tracking, the TC work is already upstreamed in the kernel. We have patches in the mailing list for OVS. To support the offload of connection tracking and NAT, so which are in final stages of review. It's in V3 now. I hope that it will get into this OVS version, and then we can just add the offloads in the kernel. Hopefully, in the next kernel version, it will be available.
Simon, of course, is one of the people who's likely to review TC patches.
Hi, thanks for your presentation. One quick question, what kind of flow update rate and throughput you receive when you offload it to hardware?
So I haven't benchmarked this for a while, but I believe at least as of the middle of this year, it was around about 50,000 flows per second could be added and removed from user space all the way into the hardware. You have to keep in mind that this is mega flows. So it's not necessarily a new flow per connection, if you like. We would, yeah.
I know Mellanox and Intel prefer RT flow to offload flow processor. So why Netronome doesn't select RT flow?
So the question, Netronome has been working on this for quite a long time, and it actually predates the work on DPTK. Netronome certainly could support the DPTK offload, but we choose to focus on the kernel because we just believe it's a good solution for the problem that's being solved here. We believe that when it's using the kernel, if the system is idle and the hardware is handling all the packets, then the kernel does essentially no work. We don't need to devote any resources. And we feel this is a good match. We also appreciate that DPTK is a good match for some people, and we are considering to support that in the future.
We have more time for questions.
So the megaflows, they don't allow overlapping. So there's no priorities. but I could imagine a situation where the flow is more specific than the hardware allows. And so what are the failure cases in which only some of the offload can be done, but not all of it? If that makes sense.
So a drawback of this approach is it doesn't really allow for partial offload, either in the matching case or the action case, or putting as the current DPTK solution does the matching hardware and the actions in software. So it's very coarse-grained in that sense, is that either the flow is entirely in hardware or it's entirely in software. But with respect to your specific question about a match which is not aligned with the capabilities of the hardware, at least for Netronome, this is not a problem because we basically designed them to work the same way. And I think that is probably the case for the other vendors too, that there is not so much mismatch there, but I won't speak for the other vendors.
Still have time for more questions.
One of the arguments against smart NICs in general is that if we have a lot of traffic, east-west traffic within the node, between VMs or containers or whatever the case may be, the traffic has to go over PCI bus to the hardware and come back up. So do you address that, or do you have a way to do the fast path in software to allow traffic to go within software and stuff coming to smart NIC?
So for east-west traffic on the same node, I agree with your problem statement. I think at this point, at least from an upstream perspective, there's no great solution for this. I think at this time, making use of the memory bandwidth of the system and not passing it over the PCI bus would make some sense. But in order to do so, I think the best solution is maybe not a great solution available is to have multiple devices inside the VM and for the VM to actually choose which way to forward the packet. I also think that as PCI capabilities increase, this problem may become moot, but I do think we're not there at this time.
All right, one more question here.
Hi, Simon. This question is from William 2. He's in the Blue Jeans chat. And he asks, is VDPA supported in Netronome NICs today?
We have it working in the lab. It's not a limitation of the hardware. It's a limitation of the application firmware. So yes, we have it working and it's supported in that sense, but it's not available. It's not GA, if you like.
All right, one more question.
I think I covered that in my talk about this partial actions offload, which is not supported by RT flow and seems like it's not supported with TC. There are some really important use cases where we should really think about how to cover that. Do you have any thoughts on partial action offload?
I agree that it's very important, and I don't have any specific ideas of how to address it. And yes, let's talk.
Let's thank our speaker.